Hi, my name is Huet Kasa. I'm a PhD student at University of Michigan. Today I will be presenting our work that focuses on efficiently mapping applications to heterogeneous systems. Today there are diverse applications that we use in every day of our lives. To name just a few, we use machine learning in healthcare, graph analytics in social media, and so on. Although this application help us in every day of our lives, they impose challenging computation and data access requirement. To overcome this challenge, the solution so far is to build custom hardware. We now have units such as GPUs, FPGAs, TPUs, and if application X requires an accelerator, then we build custom hardware for it. This has helped us to gain massive speed up and energy efficiency. While it might seem like accelerators are going to solve all of our problems, they come with their own limitations. The first one is because accelerators are built for one application, they have limited programmability. And this makes them to require specialized design, testing, and manufacturing, which is too expensive. As a result, even though we want to build an accelerator for all applications, what we are going to end up having is many applications and very few accelerators. So we need to run multiple applications on fewer reusable hardware units. Now the question becomes, how can we have few accelerators and many applications and still get the benefit of custom hardware? To solve this problem, we are developing a tool called Chip Advisor that is going to help with leveraging few accelerators to run many applications. To give an overview, let's say we have multiple applications and hardware units. And Chip Advisor is an analytical model that takes both properties of application and hardware and decide where to run all given applications. This helps with mapping applications to the best existing accelerator, telling us which hardware unit is going to give us the best performance or energy and efficiency. Or if all available accelerators are not meeting our requirements, it will guide us about what type of accelerators we should build in the future. Our design strategies are to first start with studying properties of application that makes them suitable for a specific type of microarchitecture. Then do performance analysis on an existing platform. The last step will be to correlate properties of applications and their performance on available platform to build the model. Then if we have a new compute platform, then we need to do performance analysis again. And if there arise new set of application, then we will analyze application properties and continue with step 2 and 3. To use our model, we first need to measure application properties of the target application, and then run our model to get prediction results. To study important properties of application, we adopted previous work where they noted applications share common computation and data access and communication threads. The list on the left shows common algorithmic kernels. And the study shows that most applications use one or more of the common kernels, and complex applications can be decomposed to multiple of these algorithmic kernels. We use these kernels for our studies, hoping that they can generalize for most applications, and they will help us to capture properties that can generalize for all applications. To select the properties to use for mapping, we started with the question of what inefficiencies arise in application that motivate the use of custom hardware. To investigate this, we used V2 amplifier to find inefficiencies in CPU code. And the results showed that most of the inefficiencies come from compute and memory bound. When we break this further, bottlenecks in the compute bound are requiring more compute resource and dependencies, and bottlenecks in memory are high latency and insufficient memory bandwidths. Here we have a list of inefficiencies and hardware solutions for each inefficiencies we identified earlier. But to find accurate mapping, what we want to know is what properties of application can be used to guide in selecting the right hardware to avoid inefficiencies. To do this, we identified intrinsic properties. So the relationship now becomes if an application has parallelism to avoid lack of resource, we should map it to compute unit with more we should map it to a hardware unit with more compute unit and so on. And the 5 intrinsic property here are what we're using for mapping. These are parallelism, synchronization, control flow, and temporal and spatial locality. Note that these intrinsic properties of application are independent of hardware and they characterize the nature of the application. Now I'll talk about measuring. To measure parallelism, we counted the number of active elements that can run concurrently at a time given infinite resource. And synchronization will be the number of time the active elements or threads will be communicating. For control dependency, we measured it as fraction of control instruction. For the memory properties, temporal locality will be 1 over reuse distance, where reuse distance is measured as the number of access between accessing the same address. And spatial locality is measured as 1 over average stride. The next step will be correlation. The data generated for correlation takes the kernel with diverse pattern with various data size and type. We use diverse data set per application because properties of application can sometimes change for a different input. Then we measured intrinsic properties as discussed earlier, and we performed performance analysis on CPU, GPU, and FPGA. The data generated looks something like this, where we have 5 of the intrinsic properties, then speed up over CPU, then the best target platform. To correlate the input intrinsic properties in the output speed up and best platform, we took machine learning models. We tried out various machine learning models, and as we see in the graph, tree-based models can give us up to 98% accuracy. For the future, we will be adding more data, and we'll try to see if neural networks can help more. We further tested our model on application that it has never seen before. To do that, our experimental setup looks like this. We use Intel Xeon Gold, and for GPU, we use 1080 Ti, and for FPGA, we use Area 10. We trained our model using MaxSuite kernels and micro benchmark that we created. And for testing, we use applications from different domains such as K-means, Barnes-Hut, CNN, multi-layer perceptron, and so on. And here is the performance analysis result for the testing kernel. The y-axis shows speed up over CPU, and the circle shows ChipAdvisor's selection. As we see here, ChipAdvisor can accurately predict best performance for new application that it has never seen before. Using ChipAdvisor, we can accurately predict where an application will run fast without executing the application on each platform and without optimizing application to all specific target platforms, which would have been very time consuming. We believe our accuracy comes from the intrinsic properties ability to characterize the application. We will further investigate some of the applications that are mispredicted in the future. Other than predicting the best platform, our model can give an estimate of performance relative to CPU. As seen on the graph, most of the circle overlap, and the greater the overlap, the greater the accuracy, which shows that we can estimate performance with certain error margin. In the future, we will also be working on improving the accuracy of the estimated performance. To conclude, we analyze computation and data access properties of application, and we build an analytical model that can predict the best computational platform and estimate performance. And doing this, we we achieved 98% accuracy. In the future, we'll include more kernels for testing and training, and we'll be mapping more complex applications that can benefit from using multiple platforms. And we'll also investigate efficient way of communication and coordination in heterogeneous system based on data access and communication pattern of application. This will be the end of my presentation. Thank you.